Hello everyone, my name is John Stefan. I'm a PhD student at EPFL in the Distributed Computing Laboratory, and today I'll be presenting the work of our group on the topic of combining privacy and Byzantine resilience in distributed learning. This work was done by Rashid Gerawi, Nirupam Gupta, Raphael Pinot, Sébastien Rowe, and myself. And in particular, I'll be presenting our most recent paper that was recently accepted to PODC 2021, which is called Differential Privacy and Byzantine Resilience in SGD. Do they add up? I'm going to first start by talking about machine learning. We all know machine learning. It's a hot and evolving field. It's mainly about the analysis of data and having computers learn models by themselves in order for them to make accurate predictions on unseen data. And we all know that we are currently living in the big data era. So huge amounts of data are being generated daily all over the world in different locations. And that, coupled with the fact that training data is usually expensive to share and private and sensitive, motivates the use and deployment of distributed learning. There are two main architectures for distributed learning. We first start by the centralized architecture, also called the parameter server model, which is the one we adopt in this work. So we basically have two entities, the computing server and the different workers, which also hold the data. So these different workers will be sending in each round of the training model-related information concerning the training data to the computing server. The computing server will aggregate all received information, update the model locally, and then send the model updates to the different workers. And this continues in each cycle. And there's a decentralized architecture as well, in which all nodes are the same type of nodes. So all nodes are data holders, and they all communicate together in order to train a joint machine learning model over the collective training data set of all the different workers. And in this work, we're going to use the most widely adopted scheme for distributed learning, which is the distributed stochastic gradient descent in its most popular form, the parameter server model that I just explained. So we have the workers in green, we have the server in blue, and in every round of the training, so what happens is that the workers will be computing gradients of the loss function locally over batches of size B. The gradients will then be sent by the workers to the server unencrypted. The server will then aggregate all received gradients, typically by averaging them, and then will use the standard SGD update rule to update the model weights W in order to get W prime. This is the model update step. And then the parameter server will broadcast the new weights W prime to all workers, and this goes on for further rounds. Now, in what I just presented, we can clearly identify two very common threats, a security risk and a privacy risk. Let's start with the security risk, and we call it the Byzantine threat. So in everything I just explained so far, there was this implicit assumption that all workers are correct and they will be sending correct estimates of the gradient. But what happens if some workers start misbehaving like this one and sending faulty gradients instead of correct estimates of the gradients? So in order to account for this particular threat in our threat model, we consider some workers to be Byzantine, and we represent them with this red devilish icon. And these Byzantine workers may collude, and we assume that their main objective is to prevent the aggregate model from learning. Now, the privacy threat is mainly due to the sharing of unencrypted gradients by the workers to the server during the learning, as I said earlier, and these gradients that are sent unencrypted can be used by the parameter server and any other third party that has access to them in order to violate the privacy of the training data and infer sensitive information about the training data of the honest workers. And in order to account for that particular threat, we consider the parameter server in our model to be honest but curious, honest in the sense that it will not deviate from a correct execution of the protocol when it comes to aggregating the incoming gradients. However, it is still curious in the sense that it will use the different gradients that are sent to it in order to violate the privacy of the honest workers. Now, These two threats have been mainly tackled like in a orthogonal fashion independently. Not much work has been done on the combination of both threats, and that is actually exactly the objective of our paper, is to study whether Byzantine resilience and privacy can actually coexist in distributed SGD, while not losing the utility of the machine learning algorithm and having a desirable level of final accuracy. So our main contribution and finding is that we show that it is quite impractical to combine privacy and Byzantine resilience in distributed SGD. And by impractical, we mean specifically the batch size that is used by the different workers to calculate gradients, so denoted by B. It should be in the order of omega of square root D, where D is the number of parameters of the machine learning model to be trained. And now we all know that in state-of-the-art machine learning models, D can take huge values, as can be shown in this table here, where D varies from 18 million and it can go up to 175 billion. And the corresponding batch size should be in the order of, like, it can go up to in this 400 of thousands of data samples, and we can clearly see the impracticality and computation inefficiency of such an approach. And so now that I presented to you the findings of our paper, now I'm going to present to you why is that the case? Why are they so hard? Why are privacy and Byzantine resilience so hard to combine? And where does this dependence on D come from? So in order to do so, I will first recall the model setting with a bit more details. So we have the parameter server model. We have a total of n workers. Some of them are honest, and there is up to f Byzantine workers at most. The parameter server is honest but curious. And so the honest workers are supposed to send unbiased estimates of the gradient. We assume that they have access to a true gradient estimator, capital G. The Byzantine workers, we assume that they can send arbitrary gradients. So they can send correct gradients, maliciously crafted gradients. They can send basically anything, which covers all possibilities. And since we have Byzantine workers, the parameter server can no longer simply average incoming gradient. It has to use a certain Byzantine resilient gradient aggregation rule that we also call GAR to aggregate the submitted gradients. And we recall also that the gradients are of dimension D. Now, what does it exactly mean to have a Byzantine resilient gradient aggregation rule? So a GAR is an algorithm that is executed on the parameter server. For now, let's think of it as a black box. So obviously, it takes as inputs the gradients that were submitted to it. In this example, we have 3 honest gradients and 1 Byzantine, and then it will output a gradient as a statistical aggregate function of all the input gradients. And for a GAR to be Byzantine resilient, this would intuitively mean that the output gradient should be sufficiently close in direction to the true gradient that is the true gradient, like without accounting for the Byzantine workers. And several Byzantine resilient GARs have been introduced by the community from 2017 with Chrome, and then came Median, and then MEMAD and Boolean, and recently minimum diameter averaging, also called as MDA. And now, in particular, in order to give some theoretical and mathematical background to this notion of Byzantine resilience, we adopt in our work the now classical notion of alpha F Byzantine resilience. So what does it mean for a GAR to be alpha F Byzantine resilient? It means that in a system that can tolerate a maximum of F Byzantine nodes, the angle between the output gradient and the true gradient is bounded by alpha, where alpha is a real number between 0 and pi over 2. So we see intuitively that the smaller alpha is, the stronger the resilience, because it means that that the output gradient and the true gradient are very close in direction, and the output gradient is kind of converging to the true gradient. Now, in the next slide, I present to you the variance to norm ratio condition, which is basically the only theoretical condition currently existing in the literature that we can use in order for us to check for alpha F Byzantine resilience, or verify it, or make sure that a certain GAR actually satisfies alpha F Byzantine resilience. And what is this condition in a nutshell? It basically says that the standard deviation of the submitted honest gradients should be upper bounded by the norm of the expected gradient times a multiplicative factor k of nf, which is so it is obviously a function of nf, but it also depends on the guard that is being used. Here I show some examples of the value that k of nf can take depending on the guard that is used. And our main concern here is whether or not this definition of alpha F Byzantine resilience actually complies with privacy. And in order to do so, actually, we adopt the gold standard notion for data privacy in deep learning, which is differential privacy. Here I present a simple illustration about what differential privacy does. So in a nutshell, if we have, let's say we have some data structures that are, they can be data batches, databases, what have you. And let's assume we have a certain query or algorithm to be executed on top of them to get some output. Now, enforcing differential privacy on that framework consists in having a randomized mechanism that adds a some random noise to the output of that query, such that so that the probability distribution of the outputs computed on adjacent data batches is statistically close, as can be seen here. And by data batches, I mean batches that are exactly the same, but differing only with one data sample, as can be seen here. So these two batches are exactly the same, except for the last sample. Here we have S, and here we have S prime. Now, to give some mathematical intuition or explanation, again, we also adopt the epsilon delta version of differential privacy, which is the most common version in deep learning. And epsilon and delta are our privacy parameters that control the privacy guarantees that are provided by differential privacy. We call them the privacy budget. And as we can see from this expression here, that as epsilon and delta decrease, the stronger the privacy and the better the privacy. And also reasonable privacy budgets nowadays for epsilon and delta, they should lie in the range 0, 1. And how is this differential privacy ensured? It's usually through perturbing the gradients via the Gaussian mechanism. That's what we do in this work. So basically, every worker will inject a noise sampled from a normal distribution of variance S squared to each coordinate of the gradients that are calculated locally. And S squared is proportional to log of 1 over delta divided by B squared epsilon squared, B being the batch size, and epsilon and delta being the privacy budget per learning step. Now the total variance of the noise accounting for the d different coordinates of the gradient would be d multiplied by S squared. So it will be proportional to d log of 1 over delta divided by B squared epsilon squared. And now what happens mathematically when we try to combine simultaneously differential privacy and alpha F Byzantine resilience? So here I show you again the VN, the variance to norm ratio condition without dp. Now, when we introduce dp to the equation, the variance of the standard deviation of the honest gradients should be accounted for with actually the variance of the noise that is injected, and that is what we represent here, C being the proportionality constant. And actually, what we show in this paper is that if we try to enforce these two conditions, or actually the variance to norm condition, if we try to enforce this condition to be satisfied for the several gradient aggregation rules, this results on B being, on the batch size B, being in the order of square root D. Here I show, for example, for crew, median, and Boolean, B would be in omega of square root ND, where N is the total number of workers. And for MDA, B is in omega of square root D times F over N minus F. These results are also adapted, can be adapted for any alpha F Byzantine resilient guard that exists in the literature. And we clearly see how impractical this is for large models where D can take very huge values, as I recall here with this table. And actually, we conducted a set of experiments that validate our findings on even on small models where D equal only 69. So let's see, what do we do here? So these are the experimental results. We take the phishing dataset and we train a logistic regression model in a distributed framework in two scenarios. So without privacy and in a private scenario with epsilon equals 0.2 and delta equals 10 to the minus 5. And in each case, we compare the blue curve, which is the no attack case. So when there are no Byzantine behavior in the network and we just average the received gradients at the server, we compare this curve with two additional curves which correspond to the cross-accuracy curves when there are state-of-the-art attacks executed by the Byzantine nodes. These attacks are the little is enough and fall of empires. So what we see here is that with a small batch size of 10, in both private and non-private scenarios, the attacks are able to hinder the learning, and so the models do not learn at all. And even in the private scenario, with no attacks, the cross accuracy decreases compared to the non-private scenario. Now, if we increase the batch size by a factor of 5 so that it becomes 50, we already see improvement in the non-private scenario. So all attacks are successfully mitigated. And in the private scenario, the attacks are still hinder the learning. We see, for example, especially the orange curve, which corresponds to the little attack, the model does not learn, so it stops learning right away, and the cross accuracy stagnates at less than 60%. And by increasing B even more, the first value of B or order of magnitude of B that gives us a successful combination of differential privacy and alpha F Byzantine resilience is for B equals 500. We see in both scenarios that actually the attacks are successfully mitigated, even in the private case. And to understand why B equals 500 is a relatively large value, we see here that we conducted our experiments on the phishing data sets, which is comprised of almost 11,000 data points. And since we are doing since our distributed system has a total of 11 workers, having a batch size equals to 500 actually corresponds to having half of the data set per worker, highlighting even more the impracticality of such a huge number for B. Now, to sum up, what we showed in this presentation and in our work is that the classical approaches for guaranteeing differential privacy from one side and alpha F Byzantine resilience from the other side do not add up at all. But this does not necessarily mean that this combination of these two notions is impossible or impractical in general. In fact, this is mainly due to the fact that this VN ratio condition, the variance to norm ratio condition that I explained to you earlier, is a strict and conservative condition to test for alpha F Byzantine resilience, potentially explaining the emergence of this dependence on the number of parameters of the model denoted by D. Thank you a lot for listening. I put on this slide the link of our paper on arXiv. I invite you to please go read it. It's a very interesting work. And I also put below that my email. Please do not hesitate to contact us in case you have any questions or in case you would like to discuss some ideas regarding the paper. We would love you to do so. And thank you again for listening.